Hello everyone. In this video, I'm going to walk you through question Q5 of the exercise, part 1, RF technology homework assignments. The questions ask you to match the low impedance 115 ohm to a 50 ohm transmission lines. So what is the characteristic impedance of the single section quarter wave transformer to perform this method? So this is part A of the question, and then part B of the questions as the percentage bandwidth of the quarter wave transformer if we want the magnitude of the input reflection coefficient to be lower than 0.2. And finally, we need to design a binomial matching network with 3 stages, n equal to 3. Okay, so this is the question. It looks difficult, but it doesn't. It's not difficult at all. And I will update the lecture slide for part C of the questions. We have already got the lecture slides for part A and part B, but we don't have the lecture slides for part C, but I will update it. Okay, so now we are going to stop the recording, stop the sharing, and then I will bring you back to the whiteboard. So part A. So you have a 50 ohm line and you need a quarter wave transformer, and you are going to merge VL equal to 115, and here is the characteristic impedance of the transmission line. So what is the characteristic impedance of the quarter wave transformer? So the length here, beta L, is equal to 90 degrees, or pi over 2. So quarter wave transformer is just a transmission line with the length 90 degrees, and the characteristic impedance is designed to match Enoch and Leo. And if you remember correctly, the characteristic impedance is given by the source, but the source is equal to the characteristic impedance of the transmission line, 50, and the load is 115. So you will do it carefully. 115 times 50, you will get 75.829 ohm. So this is part A of the question. Part B. Uh, we need a percentage bandwidth. What it means here is uh, yeah, the bandwidth. Right? In my lectures, look, you probably know that uh, when beta L is not equal to 90 degree, but just close, then we can use the minimum requirement of the refraction coefficient, 90 degree. Sorry, this one is according to the question. What of my tool? Then we can calculate the fractional bandwidth. The fractional bandwidth can be, first of all, we need to calculate the length first, the length corresponding to beta m. So let beta is equal to BL, and according to my notes, cosine beta m, which is beta L corresponding to 0.2, the refraction coefficient, is given by so this is the formula I have given in my notes. But you want to find beta L. So what it means here is if you plot the refraction coefficient, the magnitude of the refraction coefficient, then what you will get here is at exactly 90 degree, you will get a resonance here. So this is beta L, or or just theta. You will get exactly. So beta M represents here. So beta M, or you can say uh, uh, beta L M. So in order to calculate the bandwidth, you need to uh, find this formula. So beta L is equals to 2 pi over lambda times L, where L is the length. At different frequency, the length will be different. So if you do it carefully, the velocity is not going to change. So this means beta m is equal to 2 pi fm, which is the frequency. And then the L is not known. And similarly, at exactly the resonance, and we got the length here exactly pi over 2 times lambda. So pi over 2 times lambda. So in other words, theta m divided by theta naught is equals to theta m over f naught. And as I told you just now, theta naught is pi over 2. Theta m is equal to this. So this means theta fm is equal to 2 over pi theta m, and then times f naught. Theta m can be found from this formula. And remember, we need to find the fractional bandwidth. Fractional bandwidth can be calculated from here, delta F. And for example, we corresponding to this one, F naught is F naught. So we need F divided by F naught. And this corresponds to beta M it should be 2 times beta M minus beta naught. So this is delta F and then beta naught. It's better for me to use different way to express it. It should be beta M minus beta naught and times 2 divided by F naught. So this is the fractional bandwidth. Yeah, imagine, right? This is Fm and this is F naught and this is uh, uh, the the other F naught times 2. Yeah. So if this is the case, then you get 2Fm over L. And then minus 2. Or it could be negative, right? So depending on which side is larger. So it may be 2 minus 2 Fm L naught. So in other words, you need to substitute F naught Fm into this equation. Fm, so 2 pi beta m, and then F naught. So from what I can get here is 4 pi beta m. So the fractional bandwidth can be calculated by the length of the transmission line. The length is given by uh, beta m, and this will become 4 pi, and then cosine arc cosine. So in other words, this is the formula for the fractional bandwidth. So we can use this formula to find out the fractional bandwidth. So I'm going to clean up the whiteboard and we will continue with question B. So this is our divider formula. This is what we have here is our divider formula. Right? I'm going to write down here. The fractional bandwidth is equal to 2 minus 4 over pi, and then arc cosine. And depending on the value, we need the absolute value. So if you substitute the value here, 0.2 minus 1.2 square, and then 2 times 50 times the low impedance 115 minus 50. So what you will get is 0.632. So this is the fractional bandwidth. Now part C, so this is part B. Part C is tricky, but actually, if you know the formula, it is very easy and surprisingly easy. I can tell you the formula without going through the lecture slope. And the formula for what the question asked for is a three sections, multiple sections of quarter wave transformer. So in this case, n is equal to 3. So we have 3 sections. So one section, and then another section, and then another section. And they are all 90 degrees. The length here is lambda divided by 4. Lambda divided by 4. Lambda divided by 4. And they want you to match the low impedance 115 ohm. And the source impedance here is 50 ohm. So this is what the question asks for. So we don't know the characteristic impedance, and we are going to work it out. So you might wonder, what is the formula? The formula is so simple. N minus 1, small letter n, is equals to the low impedance and the source impedance. And then N C N divided by 2N. So this is the formula you need. N combination N represents N and then N minus N factorial and then N factorial. If you don't want to do too much calculation, you can use the Pascal triangle to work it out. So using the Pascal triangle, we can say 1, 1, 1, 2, 1, 1. So this is n equal to 2. And n equal to 3, sorry, n, big N. We have 1, 3, 3, 1. So this one is NC0. This one is NC1. And this one is NC2. And this one is, sorry. I should use different way to express it. Hang on a minute. Yeah, let me rewrite it. Now I'm going to calculate this without going through too much calculation. I'm going to use a Pascal triangle to work out capital letter N, C, and then small letter n. So 1, 1, 1, 2, 1, 1, 3, 3, 1, 1. So this value corresponds to 3C0. And this value corresponds to 3C1. And this value corresponds to 3C2. This one is 3C3. So I hope you got it clear. Now, So for n equal to 0, and we will substitute to this formula, then we get 1, and then Z naught is 50 ohm, yeah, and then this one ZL is equals to 115, Z naught is equals to 50. Then uh, 3 Z naught and 2 to the power 3. So I got 115 1 over A, which is 1.1097. So in this case, if you rearrange the equation, and Z naught is 50, and from here you will get 55.686 ohm. So this means if this is Z1, then this will be 55.49 ohm. Okay, when n is equal to 1, and substitute this to the formula, and then 115 50, and then 3C1, and then 2 to the power 3, and I got 2 3, and then A. So from what I can get is 1.3666, and Z2 is equal to Z1 times, sorry, this to be 1, Z1 times 1.3666, and Z1 we have calculated. So from what I can get is 75.82, and n equals to 2. This is the final one, and substituting to this formula, and then 115, and then NC2. I mean, 3C2, 2 to the power 3, so we got 1.3666 here as well. So this means Z3 is equal to Z2 times 1.366, but Z2 is 75.82. So what you will get here is 103 on 0.63. So you got all the answer. So this is Levy and this is zero Levy. And from what I can get, 75.8. And here 103.63. So this is the answer to part C of the question. You need the free section transformer construct like this, and this will give you an extraordinary result. If you don't believe that, I'm going to show you by simulation. Let's see. So this is the I'm now showing you the simulation window. And the lower diagram belongs to part A of the question. I have used only one section of the quarter wave transformer, and the low impedance is 115 ohm. The source impedance is 50 ohm. And in part C, we were required to make a multi-sections quarter wave transformer to match the low impedance R11, is 115 ohm to the source impedance 50 ohm. And if you do a simulation, they are all quarter wave. The wavelength is uh, a quarter lambda. So if you do a simulation surrounding the resonant frequency, so this is what you are going to get. The red one here represents the refraction coefficient for a single section quarter wave transformer. The blue curve here represents the refraction coefficient for three sections quarter wave transformer. And you can see that the bandwidth for the multi-sections transformer is much better, much wider. So if you have further questions regarding this question, please leave your comments to the section, to the comment section of this video. Thank you. Bye bye.